Thank you. That's it. Hello? Hello? Okay. Hi, everyone. I am Li He from Lambda Group of Nanjing University. Today, I'm going to talk about making intelligent agents learn to coordinate with anyone. First, let's talk about cooperative multi-agent reinforcement learning, CMARL. CMARL plays a promising role for many real-world multi-agent problems, including multi-UAV control, autonomous driving, and so on. Classical CMARL methods trains the agents to coordinate with each other and finish the task. And these methods test these same agents in the same situations. However, real-world situations come with exceptions. Specifically, the agents in the system may change during testing. For example, the agents may malfunction and we need to replace them to fix the multi-agent system, and some agents need to coordinate with different humans, like the online human players in electronic games, human drivers on the road, and so on. To fill the huge gap between the classical methods and the mentioned real-world scenarios, a promising idea is to let agents be prepared for the exceptions before testing. Specifically, the agents need to learn with as many diverse teammates as possible during training. As the number of all possible teammate policies could be large, we can only train the agents under limited storage space and training time. A key consideration here is that these diverse teammates are hard to find manually, and we need to generate them with some efficient methods. Recently, some methods are proposed to generate the diverse teammates and train the agents. So, what is their performance? What is the coordination ability of their agents? When these agents are paired with some unseen teammates, they may fail. Here is the experimental results of some related work. As shown in the red box, these agents do not perform well with some unseen teammates. Here is another related work. We also conducted experiments to prove this phenomenon. For example, the method FCB here fails to coordinate with unseen teammate number 3, number 4, and number 7. Why do these methods suffer from limited performance? We observe that all these methods have something in common. First, they need to manually decide the number of teammates to be generated. For example, FCB sets the number to 32, Tragedy sets to 12, and LiPo also sets to a fixed number. Second, these methods train this set of teammates with extra diversity objective. FCB simply uses random network initialization and different checkpoints. Tragedy adds a regularization term to the policy learning of the teammates. And LiPo induces diversity by increasing the compatibility between the teammate policies. Here's the problem. Remember that our final goal is to develop agents with strong coordination ability. But these methods, when they try to induce diversity, they only consider teammates, but without considering the agents themselves. Finally, they train the agents to coordinate with these teammates. Now let's further analyze these issues. First, we don't know the optimal number of teammates that we need to generate. Would 8 be a good number, or is 32 a better option? We don't know. Second, they induce diversity without considering the agents themselves. In other words, their teammate generation is teammate-centered. The result is that these teammates may be diverse, but they also may act equally with some agents. And they can only achieve redundant and inefficient coverage of the teammate policy space, as shown in the figure. But our goal is to achieve effective coverage of the teammate policy space so that our agents can train with diverse teammates and finally can coordinate with all possible teammate policies. To solve these issues, here are our ideas. First, we do not fix the number of the teammates to be generated. Instead, we gradually generate new teammates. Second, we propose an agent-centered teammate generation process. And we try to increase diversity from the perspective of the agents instead of from the perspective of the teammates. If we solve these issues, we can achieve sufficient and effective coverage of the teammate policy space. And after training with these diverse teammates, our agents can coordinate with all possible teammates. To implement these ideas, we propose our method MACOP to answer 3 following questions. Question number 1, how do we generate teammates in this agent-centered paradigm so that they can enjoy high diversity? Question number 2, how do agents effectively learn to coordinate with these teammates? Question number 3, how to combine teammate generation and agent learning to develop an overall algorithm? For question number 1, we first train the teammates with a self-play objective. This objective is to ensure the meaningful learning of teammates so that the teammates can have the basic ability to finish the task and are capable of coordinating with our agents. Second, we introduced a diversity objective to increase the diversity between these teammate policies, as mentioned in the related work. Finally, we propose an important objective called incompatible objective. With this incompatible objective, the agents will not well coordinate with the current agents, and they are forced to find coordination patterns that are novel to the current agents, realizing the agent-centered paradigm, as mentioned before. So training the teammates with these objectives, we can push the teammates to cover new area of the teammate policy space. And eventually, if the whole space is well covered, the teammates will enjoy high diversity. Now, the teammate generation module is settled, and let's answer the question number 2. How do agents effectively learn to coordinate with these generated teammates? Can we simply store all generated teammates for the agents to learn? No. It violates the storage constraints if the number of the teammates is large. So here we propose to use the technique of continued learning. With the technique of continued learning, the agents only need to learn with the new teammates, while remembering the coordination with all previous ones. Here we select a continued learning technique called multi-head architecture. With this multi-head architecture, the agents gradually create new heads to coordinate with different teammates. One specific policy head corresponds to one class of similar teammate policies. The reference here about coordination, the continued coordination, is also one of our work, and I will introduce about it in the poster session tomorrow. Welcome to drop back. So, for question number 3, how do we combine teammate generation and agent learning to develop the overall algorithm? Here we design to alternatively generate new teammates and make the agents learn to coordinate with them. This whole alternative process continues until no more incompatible teammates can be found. And it outputs agents that can coordinate with all possible teammates. After designing our method, we conducted experiments to test it. We first designed 8 scenarios from 4 environments, including level-based foraging, predator-prey, cooperative navigation, and StarCraft multi-agent challenge. All these scenarios have distinct coordination patterns. Take the scenario in predator-prey as an example. Here, there are 2 predators. One predator is controlled by our agent, and the other predator is controlled by the teammates. Both predators need to catch the prey. It could be a simple question, but there are 3 prey in different positions, and the predators need to catch the same prey to succeed. Otherwise, if they split up, they fail. Now, we visualize the teammate generation process of our method in this scenario. As shown in the figure, in iteration 1, our teammates have not learned to catch the 3rd prey yet. But with our teammate generation technique, in the next iteration, a new teammate in blue successfully learned to catch the 3rd prey, which is a completely novel behavior. To further validate the effectiveness of our method, we compared our methods with these mentioned baselines, including Tragedy, FCP, and LiPo. I omit the others here due to the time constraint. For a fair evaluation criterion, we aggregate all teammate groups generated by all methods into an evaluation set. For each method, we pair the agents with all teammates in this set for testing. As shown in the table, in all 8 scenarios, our method MACOP achieved the best performance in 6 of these scenarios and achieved the 2nd best performance in the other 2 scenarios. So the overall performance of MACOP is the best among all methods. And we improved the performance by 80% compared to best baseline. The results shows that our agents have strong coordination ability. Furthermore, we collect a set of unseen teammates to pair with the agents of these methods. As mentioned before, some baseline methods like FCP, Tragedy, and LiPo fail to coordinate with some unseen teammates, while our method MACOP successfully coordinates with all of them. In this study, we present a novel approach MACOP, which finds a new way to generate diverse teammate policies and train the agents. Empirical results validate the effectiveness of our method. Looking ahead, we will continue to explore the field of cooperative multi-agent reinforcement learning in open environments, and recently, we conducted a survey of progress on this field. We review CMAR in classical environment settings to open environment settings, and we provide potential research directions in future research. Welcome to follow our work. Here is my homepage and my WeShare account. Welcome for communication and cooperation. Thanks. I will be happy to take questions.
As you mentioned in your presentation that you said that all the current methods cannot make coverage of the partner space. I'm curious about how the methods have any mechanism or how you evaluate that you can ensure you coverage the whole partner space.
Okay. First, we propose here in the part 1 of our method, we propose the incompatible objective to force the teammates to not well coordinate with the current agent so that they can find new coordination patterns every time. So the coverage of the teammate policy space is also increasing in every iteration. And we also provided some proofs, some mathematical proofs in our paper. But I apologize that I did not include it in my presentation here. So the answer to your question is that yes, our method can ensure that we can cover the teammate policy space.
So what is how you define the whole coverage? Because I think in the real world that
we cannot say that we have to cover all the unseen teammates. It's impossible for any person to do this.
We define coverage as follows. Now we have our ego agents, right?
Yeah.
And our ego agents can coordinate with different teammates. If we can find another teammates that our agents cannot coordinate well, it indicates that our teammate has not covered the teammate policy space.
Well, it is similar to the link post definition that if I cannot coordinate with you well, that I'm incompatible with this, so I'm like it's different strategy or like a different agent with others. So your algorithm that can find all this, right? You mean like this?
Yes. If there are still some teammates that we have not found in the teammate policy space, our algorithm will not stop until they are found.
Oh, so you like continue to grow the partner?
Yes, yes.
Any more questions? I ask one question. About the title, I think anyone is confusing people. Is it possible to coordinate with the agents who have no intention to cooperate with?
Yes. That's a very good question. Yes, the number of all possible teammate policies could be infinite, but we only care about the teammates that have the basic ability to complete a task and are capable to coordinate with our agents. Those random or dummy teammates is out of our consideration.
Okay, so I think the title should be
learning to coordinate with any
yeah.
normal ones.
Any more questions? If there is no question, and let's welcome to the second speaker.
Thank you all.